Hello students. Today in the previous class we have a little bit discussed about near field and far field. Today we will go in uh, detail so that you can get an idea that where the near field and where is the far field. It is one of the property of the antenna that in how much range or a radius value that we can get the electromagnetic signals or radiations. So that previously we discussed about the near field. Here you have seen that it is visible to you. If you count here, this is the near field, which antenna radiations is in covered this region. If you want to find out the far field that is in this domain, so that you can get far field region. And there must be some rule and the reader in the tag which the transmission will take place between those two parameters. And far field is area some distance from the transmitting at which electromagnetic wave is fully formed and separated from the antenna. In the previous slide, that signals will not be in the form of electromagnetic signals, but when we deal with the far field region, that covers that can provide us in type of electromagnetic wave. In far field, inductive coupling is not possible. Here, the radiative coupling is one of the parameters through which we can get the signals and coverage. EM field decreases by the factor of 1 upon R. The field EM field, which decreases by this rule, where R is the distance between the tag and the reader. So if we counted the tag and reader, that is the distance between two places. We call it as a radius or the distance between the transmitting and receiving antenna. Or there is some boundary conditions or boundary approximation approximating boundary between near field and far field. There are two cases. One case is defined if we are using an antenna size is comparable to the wavelength like ultra high frequencies. So the radius formula will be this one. It is visible to you that this formula which can be used for the radius purpose. Here the distance between the antenna dimension, maximum antenna dimension, D defines, F defines the frequency and C defines the speed of light, so that we can find out the radius. And in case number two, if the antenna size is small, much smaller than the wavelength, then we can call it high frequency. And for the radius purpose, we can find out this. If the antenna size is smaller, that I guess we can say that the frequency or the radius must be larger, and if larger one because of the wavelength, but it depends on the case. So if we are considering the low band distance between the and distance in feet, so these conditions can be used for the purpose that we have these type of ranges on for the near field and far field boundaries, that we can use the distance between the reader and the tag. If we are dealing with the periodic signal voltage, so here we have V of t and V naught cos omega t. We are replacing omega with the 2 pi f, and we have in power in direct current DC, that V is equal to VI and V is equal to IR. According to that, we have a power value which depends on resistance and the voltage. So that if we coming to the power of periodic signals, that we have P average is equal to V square upon 2R, and V is in a peak to peak voltage we call it. And in terms of root mean square value, that is depending on V upon square root of R, and the power is depending on this. So why are we considering this? Because we are dealing with the power in terms of antenna transmissions. So that as previously we have discussed about phase space law, that means we are dealing with the power values in this domain. Always we are using decibel describe signals with power spectrum form, we are dealing with the power versus frequency. Signal power ranges from 10 power minus 15 to 10 power 2 watts. In logarithmic notation, we find it 10 log of x is equal to x, and then we have a gain in 10 log of 10 s and p out upon p in or p out upon v. But in the voltage form, we have to use 20 log because of the power. And if we considering absolute power levels, and dBm is absolute power with the reference to the milliwatt. dBm is equal to 10 log of P upon 1 milliwatt. If we considering in watt, then we have to change it in 10 log, not change it because this is the formula, straightforward formula. We have to convert it, the DC decibel. So as previously we have discussed about isotropic antenna, so that we have to assume antenna radiates same power density in all the direction. So there is no change in the radiation or a gain value. All the directions cover similar range of gain and radiations power. So that we considering antenna gain the focus energy is particular direction. Power gain above is isotropic or dipole antenna. So that the isotropic antenna gain in dB is equal to 0 dB, and that is depend on because and practically it is not always true because we don't have a constant value of the gain in all directions, and none of the antenna can provide a 0 dB gain. We call it in all directions. This is the half wave dipole antenna, which gains 2.2 dB gain above an isotropic antenna, or we call it dBi. And this is lambda by 2 because half wave dipole, that means divided into parameters and with the feeding line. This is pattern of a dipole as we have previously discussed. Here the role of the effective isotropic radiated power is very important parameter in the antenna designing, and almost we call it in wave propagation wireless communications. That power required if we are using an isotropic antenna to get same power as the power from the main beam of the direction. So that includes transmit power and the gain of antenna. So effective isotropic radiated power equal to transmitted power in dBm plus gain of the transmitting antenna gives us our radiated power value. This is the formula which can be used to find out the EIR. When we are dealing with the dBi value, that we have to add up the value in dB, that is 2.2. If you consider this case, okay, if we have a value of 2 dB and decibel in D, that we have, if we convert it in dBi, that we have to add 2.2 in that value. Okay, so this is all about effective radiated power. And also we have in previous classes discussed about some of the polarization schemes, the physical arrangement or radiation. So here is a linear polarization, that means transmitting antenna and the receiving antenna polarization is similar, so that it can possibly receive the signal quality. But if we are using polarized in this form and the receiver is in this direction or vertical, this is horizontal depend. So that polarization here, the law, we call it the mismatch, because this is not completely receiving, it's almost 25% or 20% or 10% that can be possible to be occurred by the this receiving antenna or the transmitting antenna. And here is a circular polarization, that electric field rotates as a function of the time around the direction of propagation. The orientation of electric field varies depending with the time, and also we have two other parameters in this range, that right hand polarization and left hand polarization, because common reader antenna to use circular polarizations and the take to use linear, so that the system is less sensitive to take orientation. this is one of the example that when we are dealing with the reader and the take, if we are using at the reader part, that is circular polarization, on the receiving part, on the take part, which we are using a linear, that we cannot get less sensitive systems. There is a biostatic setup configuration. One reader antenna is used for transmitting and a different antenna is used for receiving. Okay, that is very much important, that we have to use some part of antenna. Suppose this is transmitter antenna and this is a receiver antenna, and these signals are propagated and also they reflected. So this setup is known as a biostatic setup. If the monostatic setup that contains similar type of reader, and so that uh, this can use for dual properties for tagging and reading. So these setups is known as monostatic configuration, that we can use a similar type of antenna for both purposes. These are the reader antennas which can be used, and these are the tagging antennas which can be used for the tags and to transmit and receive these properties. Okay, and thank you for listening this video. If you found any query related to this lecture, you can contact me through my email address, that what the problem you are facing or you are dealing with. And these type of antennas are first designed in some type of a simulation software. After that, these antennas can be implemented in the real-time scenario and printed on the through the some machinery. So hopefully you get some idea, and these lectures are very important in terms of your final exams or your vivos related to the, so that you have to study very focusedly, so that if you found any query related to the lecture, I'm repeating again, because you're not watching these videos, and maybe it can be a problem for you, that in terms of your exams, in terms of your everything. And good luck for your exams, and good luck for your uh, everything. Thank you. Hope to see you again soon.